So this final part of chapter 8 is about an introduction to the periodic table, and I've already been showing you the periodic table throughout this chapter, and it's hardly an introduction because we've talked about it before. But really, this is where we're going to kind of formalize our information about the periodic table and bring forward what we've already been talking about. So we know what the periodic table looks like. Looks like that. And there's a specific arrangement to the periodic table that actually has a lot more meaning in it than we would ever sort of think about on a first look. And so the idea that elements are arranged on the periodic table to display recurring properties is something that is not evident right from the beginning. We've already talked about, how they're increased by number of protons, right? And we talked about the atomic number. But there are also similarities or commonalities between the different groups on the periodic table. So we're going to talk about the periodic table and understand its arrangement to help predict some of the properties of elements. So back in the beginning, Mendeleev gets to be credited with the development of the periodic table, and his looked quite different from ours, and there's a lot of different kind of stories out there about Mendeleev and the periodic table. But I think the cool thing is that he actually left holes for things that hadn't yet been discovered, and that to me shows that he had a pretty sophisticated understanding of the way things were organized, and he did display them to show those recurring properties. He also arranged them according to increasing atomic mass. And this was a mistake that he made maybe, but honestly at the time, I don't know how you could really find fault with it. They are arranged by atomic number, not atomic mass. So what is atomic mass anyway? So we did talk about how it was not mass number, right? Mass number is specifically the number of protons and the number of neutrons. It is not that. That's what we were talking about with isotopes. Atomic mass is actually on the periodic table. If I go back to the periodic table, these are the atomic masses. And these are the numbers that we're going to deal with throughout this course as something that's useful in a lot of different ways. And so all of these numbers on here are not the mass number, but they are the atomic mass. So what the heck are we talking about with this? So a mass number, or sorry, atomic mass is basically a weighted average of all the known isotopes. And so basically atoms are way too small to weigh directly. And so we use a carbon atom as a relative measure. And so relative measure is a mass unit. It's roughly the mass of a proton plus the mass of a neutron. And that's where we get carbon 12 as the reference. And so carbon 12, that specific isotope, is 12 atomic mass units. So if we were to take 1/12 of it, that is the mass of carbon 12. And so basically what we're talking about is all the masses are relative to the carbon 12 atom. And so if we go down here, it's carbon 12. So the key thing here that I think is important, I always get a bit muddled talking about this stuff because it hurts my head, it's so small. The key thing here is that why does it not say 12 on the periodic table? Why does it say 12.01? And the reason for that, I've already alluded to in other videos, is that this is the weighted average of all of the elements, or sorry, all of the isotopes that are present in the world. And so atomic masses reported on the periodic table is the weighted average of all the masses of the naturally occurring isotopes for each element. And so in this case, the atomic mass is on the periodic table. So on periodic table, it's the average. So weighted average of all isotopes. And if we were to deal with this for carbon specifically, it is that 12.01 that we can see on the periodic table. So that's atomic mass. Atomic number is the location on the periodic table. Or we also talked about this as the number of protons. And that never changes. So for carbon, it is 6. The mass number, this was the perfect world. It is the number of protons plus the number of neutrons, and it depends on the isotope or the specific atom that we're looking at. And so for carbon, I can't say. Sometimes it's 12, sometimes it's 13, sometimes it's 14. Those are all been examples that we've had with carbon, but that's not something that we're pulling off the periodic table. It was something that developed our concept of these subatomic particles, but it's not something that's on the periodic table. If we were to take a look at the periodic table, there are properties of the groups of elements. And so when I take a look at the periodic table, a lot of the time I spend talking about vertical columns. So that can be a group or a family. So it's the ones that are reading down the periodic table. And those ones are going to have very similar chemical properties. Even if you just kind of take a look, a cursory look at it, and something that we've already talked about, the common ions formed, I'll pick a different color, all of the ones in this column, remember that vertical arrangement, have a +2 as a common ion formed. If I do another example, everything over here, reading down, has a -1. Now you're going to be able to find exceptions to this rule, but there is a commonality of a lot of those vertical groups or families. The other thing that we could talk about is going across the periodic table. And we're going to talk about trends that go across the periodic table. And so those horizontal rows are called periods or series. And we'll talk about some of the key trends on there. If we were to take a look at the periodic table, there are 3 major divisions. The main groups that we're going to talk about would be those columns that were really, really similar. And so the columns that we have that are really, really similar, the far left, I'll see if I can highlight this. I don't know if I can. This column down here, oops, that's not going to work for me. Okay, we'll just erase all that. So this column down here, those are the alkali metals. And you'll notice they all have a +1 out here, except for hydrogen. Hydrogen's the oddball. The next one over, if I call it the next one here, are the alkali earth metals, alkaline earth metals. I always say that wrong. There's actually a correction. So this one here, this column, would be the alkali earth metals. If we take a look at the reactivity of these two, there's actually a cool video here. This reactivity of all those things in the first column, they explode in water. So anything there that you can see is highly reactive. The next major group that we're going to talk about are called the halogens. Over here are halogens. And again, you can take a look at the common ions formed as -1. And the last major group here would be the last column. And so these being the noble gases. And so those are some of the main ones that we're going to take a look at as we go through. There are some other, if we take a look through the periodic table, we have the transition metals and then the inner transition metals. So the transition metals are all these ones in the middle here. And the inner transition metals were those ones that I talked about as being sometimes down below the periodic table. Your textbook, if I find that on the one just inside the cover of your textbook has a separate series down here that are that other class that we're talking about. So those ones would be the lanthanide and the actinide series. So these ones are usually beneath the periodic table. The other key thing, and I think it's worth noting now, is that there's a steppy line that goes down your periodic table. It's not marked on here, but you'll notice it on some of the other periodic tables, like the one on the inside cover of your textbook. Now, the key thing there is that on one side, we have everything that's called a metal. Metal in chemistry. So everything from the steppy line over. And over here, we have non-metals. I didn't put an accurate steppy line on this one because it's actually, there's a little bit of wiggle room around it. But the key thing is that you have the two sides. So if we were to take a look at these vertical columns, here, we want to know which of these elements would behave similarly to calcium. And so what we're looking for are the other elements that are in the same column as calcium. And if we see that calcium is here in this second column, that would make it an alkali earth metal. And so we're looking for other alkali earth metals. If I do this right and haven't missed any, those would be the ones that would be the same. So why are they like this? They're in the same group or family. They're all alkali earth metals. The second one here, which example or which following elements would behave similarly to xenon? And so xenon is a noble gas, and so we'd be looking for other noble gases. And so when I take a look at the periodic table over here on the right-hand column, all those noble gases, xenon would be on the periodic table here. So anything else in this vertical column would behave similarly. And that's what we're talking about with these this arrangement of the periodic table. So we've got helium, argon, and radon are all examples of noble gases. So the next bit, whoops, sorry, I meant to turn the page and I flipped the document. So the next one here are a better diagram, inside cover of your text if you like, and below. The step line separates the metals and the non-metals. So you can add that to your periodic table, neater than I did on my scribbly one here. So we have metals on this side and non-metals on this side. Along that steppy line I said is that kind of gray area. Those are called metalloids. They kind of are a little bit blurry as far as their tendencies, and they're kind of different than transition metals. Transition metals, if you remember, were this bit here. They're metalloids, and they're kind of in between, if you will, the metals and the non-metals. So all metals, if you're taking a look at the general periodic table, all metals are shiny. And if you watch the video that showed how reactive sodium was in water, it is a metal, hard to think of. It's malleable, so you can kind of mold it or change the shape of it. It's ductile, which means you can pull it into a wire. It's conductive, it conducts heat and electricity, and there's lots of examples of metals that I'm sure you can come up with off the top of your head. Non-metals, in comparison, are not shiny. They don't look like metal. They're brittle, they shatter under pressure if you can get them at solid state. They're generally a poor conductor or non-conductor of heat electricity, and examples that are from beyond this step would be carbon, which graphite is an example, oxygen, nitrogen, anything that you can see that's beyond this step, including those noble gases. So the properties of metalloids, or the semi-metals, are, like I said, they're kind of in between. So they have some metallic properties and some non-metallic properties. And as an example, silicon has a shiny appearance and it conducts electricity like metal, but you can see where it is on the periodic table. It's kind of over in the non-metals, and it behaves as a non-metal in some other ways. So metals and non-metals are classic examples that create ionic bonds. We've already talked about them. The other word for anything that is a metal and a non-metal together are salts. And we'll just come back to that. I tried to kind of weave this stuff into the notes as many times as I can. Couple more things to take a look at before we round out this discussion of chapter 4. This is a nasty gang of troublemakers. I kind of personify some of these things. These are talking about the diatomic molecules. And I said that already. O2 is a molecule, but it is not a compound, because it doesn't abide by this fixed ratio idea. And so all of these diatomics are kind of in that classification. So there's 7 gases that don't hang out as a single atom. They always hang out with pairs. So they're called diatomic, so 2 atoms, molecules, and they are all gases, so diatomic gases. And the way I remember these is you can either take a look at their location in the periodic table, or I'll just be true to my own. I call them the Hofbrinkels. So it's kind of like that's their last name, like that's their name, like their gang of thugs. And every time I do this, I imagine them with David Hasselhoff's face. So hydrogen is H2, oxygen is always O2, F. Fluorine is always F2, so that's the Hof. Brinkle, Br2, is bromine gas. I is iodine, but it always hangs out with 2 atoms of iodine, so I2. In, getting to the inkle part of it, nitrogen gas, and chlorine gas. Always, always, when these are elemental, as a pure element, they always hang out with 2 atoms of that kind. So we'll come back to these because they really are, like I say, a pain in the butt. I feel like they're evil thugs, the Hofbrinkels. They're out to get you. Last little bit here is the states. And most of these things that I was talking about as the diatomics are the gases. As you can see, they're in yellow, and your photocopy doesn't come out like this, so it might be nice to color copy or photocopy these, or better yet, add them to your periodic table that you can have with you kind of at a glance. So we've got all of the diatomic gases here, Hofbrinkel, and including the noble gases. They're not diatomic, but they are gases, right? Liquids, only 2 exceptions. So technically bromine in the Hofbrinkel gang is a liquid, as is mercury. And I think that one would kind of come to mind, liquid mercury, right? At standard conditions, so standard state, and that's the important thing. I mean, all these things could exist in any state, technically, at given temperatures, but at standard temperatures and conditions, they exist in these states. And so, like I say, most of the things are solid, a few gases, and then those 2 oddball liquids.